Webinar. So I'll jump right into the topic and try to cover a little bit of every important thing that we see in production, in the opportunities and challenges in the production of cement. So first I'll give you a brief overview of what the hydrogen production today is. I'll talk about the cost and availability, the challenges with the process, with keeping the process well delivering while using hydrogen, and how we can overcome obstacles. So to start with, just for it's a general information, we produce about 90 million tons of hydrogen in the world, and most of it, if not over 95%, is hydrogen produced with unabated emissions of CO2. Meaning, to generate hydrogen today, apart from electrolysis and steam reform, methane steam reform with carbon capture, hydrogen produces more CO2 than most of the fuels, like natural gas and fuel oil. So the key thing here is, unless we use electrolysis or methane steam reform with carbon capture, our hydrogen is not doing any good to the environment. Getting back to what I told about the net zero, the participation of hydrogen in the net zero environment by 2050 is quite small. So if you see here in the graph, it's about 6%, 6 to 8%. So it's a very small participation in the whole fuel, let's say, matrix in the world. So what I want to tell is, hydrogen is not the only solution. It's just small part of the solution of the net zero challenge we have today. And if we go on the sources of hydrogen in the future, in a net zero scenario, and we are talking about 500 million tons of hydrogen, about 300 million would be produced with electricity, and we need renewable electricity, otherwise we are polluting with CO2 or emitting CO2. And the other 200 million would be with fossil fuels like methane reform or gasification of coal, but with carbon capture. Again, getting back to the future in 2050, this is, I don't know why it's repeated. Sorry, I went to the wrong slide, sorry. So pretty much we have to align costs with availability and resources and the process in the cement kilns. So we are looking to reach this small area that today it's really challenging because costs are high, we have no availability, or it's a very small availability. And regarding the process, there are some ways to use hydrogen, but we'll see that it's not so simple to replace all the fuel in the cement in a cement plant or in a cement kiln by hydrogen. Cost and availability. It depends on the technology for sure. If it's methane steam reform is one price. If it's electrolysis is a different price. If it's electrolysis, you need renewable energy. Again, otherwise you are still emitting CO2. So do you have renewable energy available, and what's its price? If we are talking about the methane steam reform, natural gas price is important. CO2 price is part of the equation as well, and it can play an important role in the economics, in the overall economics of the use of hydrogen in cement plants. And if we talk about electrolysis, do we have water? In some places, Middle East, we don't have water. So, I mean, you have water, but it's you have to use desalination. So it's an increased cost. You have to make the desalination of seawater to get proper water for the electrolysis. And do we have a distribution infrastructure? How are we going to distribute the hydrogen that's produced to the final, to the end user? So pretty much it's difficult to put a price to the kilo or gigajoules of hydrogen, because it depends a lot on where you are in the globe. So if you have renewables, non-renewables, if you have the natural gas prices, the CO2 prices, and so on. I'll try to give a picture of what we have today in terms of studies of the cost of a kilo of hydrogen. So this is the cost in different countries for the production of 1 kilo of hydrogen, assuming you have photovoltaic or panels. So if you go, for instance, in Japan, the price, it's only for production. There is no distribution, no margin. It's not a sales price. So if you go to Japan, you would have about $9 per kilo to produce hydrogen. If you go to European Union, 4.3, Canada, 6.7, Italy, France, Germany, and etc. So as I mentioned, it will depend a lot on where you are to get a reliable price for the hydrogen. Of course, the lower the cost of capital, and the lower the cost of capital, for the money, the weighted average cost of capital, and the lower the cost of the photovoltaic plant, solar panels, the better. The other part of the equation is how much can we get for the tons of CO2 we will reduce in using hydrogen. So again, if you are in the EU, there is a price for the carbon that's USD per tons of CO2 about 90. On the other hand, we have 70, 10 for Japan. Putting together, for instance, the two graphs, Japan wouldn't be the best, hydrogen wouldn't be the best solution for Japan. So you have a very low price for the CO2, and a very high price for the production of hydrogen. So you have to pretty much to combine all of this to make a study, a feasibility study, if it's worth using hydrogen and in what extent, 5%, 3%, 10%, whatever. Again, it's obvious that if you have a higher carbon price and you have programs that cover most of your greenhouse gas emissions, this is the higher here, the better. So in an exercise, assuming we have a electrolysis plant and steam methane reform with carbon capture and without carbon capture, and we use those costs for renewable energy, 70 euro per megawatt hour, which is a very good price. And if the OPEX of the electrolysis without energy, all the other costs are 2.9 euro per gigajoule, we would have a price of 9.2 for natural gas euros per gigajoule, electrolysis 39, steam methane reform without carbon capture 17, and without carbon capture 12.4. So it's still pretty costly. It's high cost to produce hydrogen. So from the economic perspective, it's still not feasible unless, as Tyre mentioned, you use it as a fuel enhancer, so you can use a small part of hydrogen of your total fuel matrix to be able to use other alternative fuels, cheaper alternative fuels. And to give a claim, just to give a flavor of what each country is doing, and I apologize to whoever is not citizen of those countries, because it's quite easy to find information from those countries. That's why I'm using it. So even in the most advanced countries, most advanced in the timeline, we are still talking of marked growth at 2030. So until 2030, we are talking about technology readiness in 2-3 years, and then start market penetration, and then the market growth itself for the use of hydrogen. And again, to give an idea of the challenges, there are about 4,500 kilometers of pipeline of hydrogen installed in the world, not installed, sorry, operating in the world, while we have 1 million kilometers of pipeline of natural gas operating in the world. So we don't have infrastructure today to distribute hydrogen in large scale. So it will take time, and it will take a lot of investments. Getting to the process, what we want in the kiln, and then I'm talking specifically in the kiln, in the rotary part of the kiln, not the calciner itself. We want process requires radiation, because it's the main heat transfer mechanism. And when I use hydrogen at 100% at least, we will have low flame emissivity and very high temperatures. So It doesn't mean we cannot use, we can use, but together with other fuels. For instance, if you have coal or you have MBM or tires or other fuels that can produce significant radiative flame, then it's fine. So here you see the effect of adding, this is gas, and then if you add coal or sand or sodium bicarbonate. So you see that the luminosity of the flame increases significantly. Here this is in a cement kiln, in fact. This is on the upper part, it's a burner using 100% natural gas, and with hydrogen will be even worse than this. And the same burner with 30% natural gas and 70% coal. So you see a huge increase in the luminosity of the flame. So this increases the emissivity, and then we can keep the kiln operating in good conditions without losing production or changing in kiln in the clinker quality. If we go for 100% hydrogen which would be extreme, we would have a longer thermal profile. We expect to have, compared to, let's say, coal flame, so a higher peak of temperature closer to the burner tip, and then a smooth decrease in the thermal profile due to the very poor radiative heat transfer of hydrogen flame. So we don't see at this stage, and not at this stage, we don't see really hydrogen as being a fuel for 100% use in rotary kilns. Naturally, hydrogen in the calciner, where radiation is not so important, depending on the calciner, this problem would be would be minimal. We expect high NOx generation as well, as Thais showed with the simulations and in the tests. Hydrogen use can lead to significant NOx, increase in NOx. So here we have a flame in laboratory. It is a lab tests, okay. 100% methane, and then increasing the percentage of hydrogen. You see that NOx increases a lot. So as of today, cost and availability, we are not there. And full substitution of hydrogen, we are not there. What we see as possible in the future is cost and availability. There is a massive investment in improvement of technologies, so the price will go down, and the renewable energy will go down as well. The electricity produced with renewable sources. We'll have to pay a price for it if we want. It will be, if you put a penalty on CO2 emissions, we'll have to pay it. So if we increase the environmental consciousness, we will do it because it's good. But there is a price. And from the process perspective, we understand that the multi-fuel approach is the only way to go, and it means use small percentages of hydrogen in the total mix. And for instance, for countries where natural gas is available, you can dope the natural gas with 5% hydrogen, for instance, which in the pipelines, I mean, in the supply line, and you don't have even to change the pipes or to make modifications to the pipeline. So this could be a possibility. So I think I am in time, and this is the last slide. Thank you.
Thank you very much for that, Renato. A really interesting presentation, again highlighting the challenges of burning hydrogen at very high levels, but at smaller levels, certainly up to 5%, it's very viable, and with existing infrastructure and systems. And I think what you said at the end there about the doping natural gas pipelines seems like a very sort of viable, very sensible approach. So for any producers out there who are using that natural gas as their primary fuel, then that's something to keep an eye on. A big advantage in some respects. And you highlighted the multi-fuel approach, which is really the way forward. Again, I think the biggest problem is the cost and the supply. Do you see that changing quickly in the next sort of 5 to 10 years, or are we looking at a longer time horizon?
I see at a longer time horizon. Prices are dropping in terms of dollars per kilo, dollars per gigajoule. They are dropping, but they are not comparable to the, let's say, traditional fuels, coal or petcoke or natural gas. It's still not competitive. But again, if there is an incentive, why not? From the economic perspective, and in terms of availability, to have a high substitution, you would need huge electrolysis plants. So I don't know, perhaps a football field or something like that, to produce a substantial amount of hydrogen. So the distribution passes through either doping, as I said, the natural gas pipelines, or installing new hydrogen pipelines, but it's in the longer term. I don't think we'll see available in scale, in a reasonable scale, before 10 years or so.
Interesting question. How much in terms of kilograms of hydrogen is required for the production of 1 ton of clinker? Is there any rule of thumb?
So one kilo of hydrogen has 120 megajoules. So if I mean 800 kilocalories, let's say, per, then we divide by A. Sorry, I'll do just the calculation here. So it will be 28 kilos per of clinker per. Sorry, let me. I'll do the maths, and I'll yeah.
Yeah, we don't want to put you under pressure. That's but that, yeah, the principles are all very clear. And I guess it's like I said, going back to the multi-fuel solution, that's the way forward. I mean, you see, it seems to be straightforward to burn in a kiln. Calciners are a different thing.
Yeah, calciners are a different thing because we don't have the constraints of the radiation. So it would be fine to reach almost 100% in the calciner, but again, it's a huge amount of hydrogen.
Yeah.
So I don't see it in the near future or even the medium term. Yeah. I don't see it. Perhaps it's better to use as a fuel enhancer, a part in the calciner, a part in the main burner.
Yeah, and that's certainly what a lot of producers are now doing. And I guess unless we've also heard of some that are setting up their own electrolysis facilities in plants. I think Rudersdorf Cemex is doing that in Germany.
But all
small
is
scale.
still, small scale, 2%, 1%, 3%. There is no high scale test I mean, high substitution rates in tests. Not that I know, at least.
Very good. Well, thank you very much, Renato, for the presentation. And that brings us to the end of this session.